now. If it is possible, you should make it full screen maybe from the view.
Full screen.
Yeah, the view.
View, just a minute. Okay.
Yes, view and full. Please click. Yeah, there's full screen mode or Control L maybe.
Just a minute.
Yeah,
full.
come. But yeah, full screen mode. Yes.
How is that?
Yeah, it's okay now.
Yeah, visible.
It's better.
Now it is visible.
Okay.
So,
yes,
so
Professor
today,
Lee, you can start.
Okay, thank you. And now the invited Professor Ayman Badawi, he will give the talk on the generalized total graph of a commutative ring. Sir, you are welcome to present yours.
Okay, thank you. Well, this is maybe the first time online in Turkey. Usually I attend conferences face to face. So I hope maybe next year I will be, or all of us will be face to face. I start by thanking the organizers and of course Professor Ikram Savas for his kind invitation. And okay, this is a talk about generalized total graph of a commutative ring with my co-author David Anderson. Let me start tell you what's all this about. How can I remove this? Okay. Here is the motivation for this talk. If you are in this business, usually all graphs are constructed from the zero divisor element of the ring. So there is a question. What about integral domains? What integral domains? They are commutative rings, but zero is the only zero divisor element. You can think of the integers, polynomials over a field, and so on. These usually are excluded because the zero divisor elements of these rings are just the normal zero, the additive identity of the group. So this is the motivation of this talk. Okay, so keep this in mind. In order to do that, we have this definition that will allow us to include integral domains when we study a graph. Oops, I went to the last page. Okay. How can I? Okay. Yeah. These are, you start from, we define a non-empty subset H of R to be a multiplicative prime subset. So if you want to follow my talk and to make sense to you, you need to know what I mean or with multiplicative prime subset of the ring. Two conditions. One condition is the closure under multiplication. Whenever you have an element A and B in H, then when you multiply them, you stay in H. And the other condition, whenever you have an element in H, call it B, I mean, whenever you have AB in H, for some element AB in R, then you want A in H or B in H. I go back to the first condition. I think I gave you the first condition wrong. I said A, B in H for every A in H and B in H. In fact, if you read it, I want A, B in H for every element A in H and B in R. And remember, the ring is commutative, So it's not matter AB or BA or whatever. And the second condition looks like the condition for a prime ideal. Whenever you have a product of two things in H, then I want one of them in H. Definitely, the set of zero divisor of any ring satisfy these two conditions. Okay? The set of the zero divisor of any ring satisfy condition 1 and 2. But as you're going to see, H need not be the zero divisor of the ring. Not necessarily. And that's the goal, or our goal in this paper is to include integral domains when we study graph. Okay? All right, and here's some observation. H will be multiplicative prime subset if and only if H is a union of a prime ideal. So choose your prime ideal randomly from any ring, and the ring now can be integral domain. And that's the interesting part. And you take the union of these prime ideal, then H will be multiplicative prime subset. Okay? Well, it's clearly, since H is a union of a prime ideal, then the set of nilpotent will be in H. And definitely H will never include unit, invertible element under multiplication here. Anyway, so our setting here, my H is multiplicative prime subset. What does multiplicative prime subset mean? Whenever you have an element A in H and B in R, then A, B has to stay in H. And the second condition, A, B in H, then one of them has to be in H. Okay, we go to the sum. Okay. All right, let me. Oh. How can I go? It seems when I am in control full screen, I cannot. Okay.
Just you can enter
Sorry?
or click. You can click the right button or page down.
Because
Page
when
down from the keyboard.
keyboard. Oh, okay.
Page down option is there.
Okay, I see. Yeah, that will work. Thank you. Okay, so what is the generalized total graph? The vertices, or whenever you want to talk about the graph, you have to define what are the vertices and how you connect two vertices. The set of vertices will be all elements of the ring R. And how do we connect? Whenever you choose two vertices, X and Y, then X and Y will be adjacent. What do I mean adjacent? They are connected by an edge. If and only if, when I add them, I stay in H. So your H is multiplicative prime subset, and the vertices are all elements of the ring. And how you connect two vertices, if you add them, you stay in H. Okay. All right, I come to that whenever I need. So we're gonna divide this talk into two parts. What about the first case as written here? What about my H? Remember, my H is multiplicative prime subset. What about if H is an ideal of R? Okay. So here in this case, we assume H to be an ideal of R. Here's some comment you read. I come to the first result. Assume H is a prime ideal of a commutative ring. Remember that usually H is a union of a prime ideal. What about if I select only one prime ideal? Then H will be definitely a prime ideal. And you let the cardinality of H is alpha, and the cardinality of the quotient ring R mod H to be beta. Then here is the structure of this graph. If 2 is an element in H, then the generalized total graph of R take away H, this set. So I'm looking at the subgraph of the generalized total graph that consists of all vertices of R that are not in H. Then I know exactly how this graph look like. Is the union of beta minus 1 disjoint K alphas. Alpha here, remember alpha is the cardinality of H. And usually in graph theory, usually you write K index by alpha. Here we just, since these graph are taken or are constructed from rings, we use alpha to be exponent. And K alpha here meaning complete graph. What complete graph? Meaning every two vertices are connected by an edge. So that means if your H is the prime and you take the subgraph of the total of the generalized total graph that consists of the vertices are all elements of R except the elements in H, then we know exactly how the graph look like. Just disjoint component, and each component is a complete graph. What about if 2 is in H? Then the generalized total graph will be the union of beta minus 1 over 2 disjoint. This notation here mean complete bipartite graph. Complete bipartite mean the set of vertices can be split into two, where let's call it set A and set B, and every two vertices in set A are not connected by an edge. Every two vertices in set B are not connected by an edge, but every vertex in A is connected by an edge to every vertex in B. This is what we call complete bipartite. And the notation is K alpha alpha. And again, in a graph theory, you use alpha alpha as an index. But since these graphs are taken from rings, we write the alphas as exponent. All right, here is a kind of interesting structure. And let me stop for a minute here. Now, what about if I take my ring to be integral domain? And I take my H to be the prime ideal 3Z. So my R is the set of all integer, and my H is the 3Z. Then I know, and 2 definitely is not in the prime ideal 3Z. Then I know what will be the structure of the subgraph that consists of of the vertices, all elements of R except, and R here is Z, take away H, which is 3Z. So if I take all my vertices to be all the elements of Z except the elements that live in 3Z, then I know how they look like. And remember that my H is 3Z. So the cardinality of Z mod H will be 3, right? Because we know Z mod 3Z, the cardinality will be 3. So 3 minus, so it will be one component, right? 3 minus 1. So you will have only one component for this graph here of Z when I remove 3Z. Okay, kind of, maybe easy, but remember, okay. All right, let me give you another. Okay, here is an assuming H is a prime ideal again. Here a complete answer, and this graph here again, how you think of it, this is the set of all vertices of this graph. All the elements of the ring are except the element in H. And again, how do you connect two vertices? When you add them, you should stay in H. So the question, when this graph is complete if and only if R mod H is Z2 or R mod H is Z3. This is when the graph will be complete. That's it. That's kind of interesting. Okay, what about connected? The graph will be connected if and only if R mod H is Z2 or R mod H is Z3. So look, if this graph is connected, which graph? I'm taking the set of vertices to be all the elements of R, take away H. If this graph is connected, then it has to be complete by 1 and 2. Okay? All right. Now, what do I mean with diameter? So I wrote that in introduction, but I think in talk, maybe you should mention the definition when you get there. Diameter of the graph is the following. You calculate the distance between every two distinct vertices. And what we mean with the distance is the length of the shortest path between two vertices. Like, let's see, you have vertex A and you have vertex B. Okay? Then the distance between A and B will be the shortest path between A and B. Like in the street language, you think of it as the minimum number of edges that you need to cross in order to go from A to B. That will be the distance between two vertices. The minimum number of edges I need to cross or I need to walk over in order to go from A to B. So the diameter, you take the maximum of all these distances. Or if I want to use analysis, maybe I should say supremum, because sometimes maximum will not exist, but supremum will. Anyway, this is, but in our case here, we can call it maximum. All right. Anyway, so the diameter of the same graph, which graph? I'm taking the set of all vertices R, take away H, and remember H is a prime ideal. The diameter has to be either 0, well, that means I only have one vertex, or 1. Well, if the diameter is 1, that means you have complete graph, or 2, or infinity. Wow, kind of interesting, isn't it? If H is a prime, these are the possibilities. You can go from one vertex to another if by this or infinity. And it will be less or equal to 2 only if it's connected. And let me remind you, when this graph is connected, only if R mod H is Z2 or R mod H is Z3. Okay, here are some results when the diameter is 0, and that's expected. R consists of, R will be Z2. When is the diameter will be 1? When the diameter is 2? When the diameter is infinity? Okay, now let me mention the definition of girth. Now you know what we mean with diameter. We calculate all the distances between vertices and we take the maximum. So what do I mean with the diameter? Girth. Girth is the length of the shortest cycle. Like you start from A and you go around and you come back to A. What is the shortest cycle? Like what will be the minimum number of edges, the minimum number of edges you're gonna go from A, go around and come back to A. This is what the girth. So the girth by definition, the minimum is 3. If you have 3, then you have a triangle, the girth. It could be sometime 4, rectangle or a square. So the girth is 3, a complete characterization for when this graph, the girth will be 3. If and only if the cardinality of H has to be at least 3 and 2 has to be in H. The girth is 4 if and only if 2 is not in H and the cardinality of H bigger or equal to. Other than that, the girth is infinity. So for this kind of graph, we don't have the shortest cycle could be 3, 4, or infinity. What do I mean, by the way, with girth infinity? That means I don't have cycle in the graph. The graph has no cycles. Okay? And of course, if the graph is connected and it has no cycles, then this is what we call a tree. But remember, the graph maybe is not connected. So the girth infinity means it means no cycle. All right. Here is some more. Okay. Still, yeah. I will mention how much time I have.
Around 15 minutes.
Okay,
15.
of course there will be, I will take only maybe 10 minutes and I leave 5 minutes if anybody has a question. I will look at the other case when H is not ideal. Because one case when H is an ideal, we're done with that. And in this case, H will be a prime ideal. What about if H is not ideal? What can we say about this graph? Then here, look, if H is not an ideal, then I can talk about the generalized total graph where H is included in the set of vertices. When H is not an ideal, then I can talk about this graph, generalized total graph of R. In the previous section, I was talking about this graph where my vertices, all the elements of R except H. But if H is not an ideal, then I can include H as part of my vertices. So if H is not an ideal, the set of all vertices will be R. And look at this result, that this graph is connected if and only if the ideal generated by H is give you R. So if H is not an ideal and yeah, here is an observation about this result here. So that means this graph will be connected if you can find some elements in H, Z1 up to Zn, where each element of R can be written as a linear combination of these Z1 up to Zn. That's exactly what I mean that R is generated by the ideal H. Each element in R can be written as a linear combination of Z1 up to Zn. Okay? All right. Yeah. Here also kind of interesting. Remember in the previous result, the generalized total graph will be connected if and only if each element, if and only if there are finitely many elements in H, call them Z1 up to Zn, and R, and each element in R can be written as a linear combination of the Zi's. Okay? Look at this result. Let n be the least integer where R, each element in R can be written as a linear combination of the Zi's and the Zi's in H. Then the diameter of the graph will be the number of the generators. Then n will be the diameter of this graph. And this is kind of interesting. It's different from the case when H is ideal. Remember, when H is ideal, diameter cannot be more than 0, 1, 2, or infinity, right? Where if H is not ideal, then we allow the diameter to be any integer. In fact, later on, or I can tell you now, give me any positive integer n, like a million. I should be able to give you a ring R where the diameter of the generalized total graph will be that million you gave me. That will be, and this is kind of total graph is kind of a little bit different from other type of graph Other type of a graph, if you study them, you see that the diameter always like less or equal to 3. Where when you talk about the total graph, diameter of the graph can be very huge. It can be any number. And as I told you, give me any number n, I should be able to give you a ring where the diameter of the generalized total graph is that number. Okay, here is some result. To calculate the diameter of the generalized total graph, just look at the distance between 0 and 1. Calculate. So what I mean with the distance between 0 and 1, count the minimum number of edges you need to cross in order to go from 0 to 1. Like, you walk on on the minimum number of edges that you walk over in order to go from 0 to 1. That will determine the diameter of the graph. Okay. Let me end up with just yeah, here is the example. Of course, this is technical. You have to check few things. My ring, as I told you, give me any integer n, I should be able to give you a ring where the generalized total graph will have diameter equal to n. And in fact, the construction, I'm using a very familiar ring. As you see, my ring, for every integer n bigger or equal to 2, let Rn to be this polynomial ring with n minus 1 variables over the integers. And here we have to select my prime ideals carefully, because remember that H will be the union of these prime ideals. You select them like here, like P0, you add these variables. P1 will be x1, and then Pn minus 1 will be xn. I mean, you look at that. This is very technical. And then we prove that the diameter of the generalized total graph of this ring is n. Okay? And this is kind of interesting. Here is the example. And look, the ring involve is integral domain. And that was our goal. How to attach a graph to integral domains. Because usually you study a graph when the ring has a 0 divisor. Okay? These are just illustrate more and more. Maybe I think I stop. That's enough. And of course, if you are interested, here is my last comment. If you want to read this paper, I gave you the address where you find it, and this is for free. You can get it for free. There will be, if you like to know more details about the proof and other things. And I would like to thank again the organizer, and in particular Professor Savas. Thank you.
So participant, do you have any question?